Hi everyone, these are the examples to go with lecture 2. And in the first example, we're just going to look at the definition of average velocity. So the question is, how long does it take to go 200 meters at an average velocity of 1.6 meters per second? And looking at the problem, you can see what the answer is going to be just from the consideration that how long means an amount of time. And so you should wind up with an answer in seconds. And to get an answer in seconds with these two numbers, you can take the 200 meters and divide by the 1.6 meters per second, because when you divide meters by meters, meters go away. And when you divide 1 by 1 over seconds, remember when you divide by a fraction, you multiply by the reciprocal of the fraction. So dividing by 1 over seconds is the same as multiplying by seconds. So if you take 200 meters and divide by 1.6 meters per second, you'll get an answer in seconds. That trick won't always work because you may have numerical factors without units that will come into the problem. But it's good to have that trick in mind as you go through this course pretty much all the time, because watching the units and hence the dimensions of the answer and the steps leading to the answer is really powerful. It gives you a lot of control over what you're doing. Anyway, without thinking about the units, though, we can just look at the definition of average velocity, which is a change in position over change in time, and use it to get the answer. So we want to, because the problem asks for how long, we want to solve for the change in time. And so we're going to do some algebra to get the change in time by itself. The first thing we're going to do is multiply both sides by the change in time. Remember, if you multiply both sides of an equation by the same thing, you haven't changed anything. You've moved things around, but the equation is still true, is what I mean. And so when we multiply by change in time on the right, we cancel both the change in time in the denominator. And when we multiply by change in time on the left, we wind up with change in time times average velocity. We want to get change in time by itself. So we want to move average velocity to the other side, or get rid of it on this side, which is the same thing, or will lead to the same thing. So to get rid of average velocity on the left, we divide by average velocity, because on the left, we're multiplying by average velocity. To get rid of it, we do the opposite, so we divide by average velocity. And again, because we want to do the same thing to both sides of the equation to keep it true, to keep the equation true. Dividing on the left means we have to divide on the right. And so on the left, average velocity cancels, leaving delta t. On the right, you wind up with delta x over average velocity. And then you plug in numbers. Delta x is the 200 meters given in the problem. Average velocity is the 1.6 meters per second. And you divide the 200 by 1.6 in your calculator to get 125. And as I was saying, meters divided by meters goes away. And you have 1 divided by 1 over seconds, which is the same thing as multiplying by seconds. So your answer is 125 seconds. And notice that the answer is in seconds, which is what it needs to be, because the question asks for how long, for an amount of time. And so your answer had better have units of time, which in this course are seconds. Or you could convert to minutes, right? 125 seconds is a little bit awkward. Minutes, 2 minutes and 1/12. So was it 2.0833 minutes? assuming I did that right. So yeah, anyway, the answer is 125 seconds, which makes sense because the question was asking for how long, an amount of time. Okay, and again, questions, at this point, I would ask the class, if I were present with you, any questions. And I'd wait a little while to see if anyone would ask a question. But if you have a question, look it over, see if you can figure it out. But then if you don't, please post on the discussion board, come to office hours. Questions are good. I was talking earlier, mistakes are good. If mistakes are good, questions are certainly good. All right. Okay, so please try these two problems. They're just using the definitions of average velocity and average acceleration. And when I say just, I mean it's not that that's a trivial problem necessarily for you, because you're doing this either for the first time or for the first time in a long time. So take your time and don't feel you have to solve it in 30 seconds. In fact, whenever I come upon a new problem, something I haven't seen before, and I try to solve it fast to show I'm better than the problem, which we all are. We're better than the problems. But if I try to disrespect the problem, I get it wrong. So take your time. Write it down. It's fine. You don't have to rush through it. So yeah, maybe no more than 5 minutes or so per problem. The second one may be a little bit longer, but don't. If it's not coming out after 5-10 minutes, I'm going to show the answers, and so you don't have to spend a really long time on it. So yeah, if you want to pause here, and welcome back if you paused. Okay, so the first problem, person walks, I'm going to show the answer now. Person walks 5 kilometers in 8.5 hours. What is the person's average velocity in meters per second? So this is just going to be plugging into the definition of average velocity, which is a useful thing to practice at this point. So yeah, definition of average velocity is change in position over change in time. Change in position is 5 kilometers. Change in time is 0.85 hours. And I didn't think carefully when I was speaking on the last slide. We also have to do unit conversion, right? Because the answer has to be in meters per second. So yeah, I might have lost some points if I just well, I would have noticed that my answer was in hours, and we usually come up with times in seconds and distances in meters, but actually, in a lot of situations, kilometers per hour is more convenient. But here, meters per second and kilometers per hour actually don't differ that much numerically, because kilometers shrinks the number of meters and hours shrinks the number of seconds. So yeah. Anyway, we are to convert to meters per second though. So we want to get rid of kilometers and kilometers starts out upstairs. So we want to divide by kilometers. And to do that, and replace it with meters. So we want to divide by kilometers and multiply by meters. And the number of meters in 1 kilometer is 1,000. So if we multiply by 1,000 meters over 1 kilometer, we have multiplied by 1, and we're good. We've replaced kilometers with meters without changing anything essential. Likewise, we want to get rid of hours and replace it with seconds. Hours is downstairs, so we want to multiply by something with hours upstairs. And we're replacing hours downstairs with seconds, so we want the thing we multiply by to have seconds downstairs. And we want the whole thing to equal 1, which it will if we choose a number of seconds corresponding to the number of hours we choose. I chose 1 hour. Number of seconds in 1 hour is 3,600. It's 60 minutes times 60 seconds per minute, or 60 times 60, 3,600 seconds. And so if you plug all this into your calculator, you wind up with 1.63 meter per second. The second problem, how much sooner would the person arrive at the end of the 200 meters in the example, having started at the same time and traveled at 3.2 meter per second? Originally, it was 125 seconds at 1.6 meter per second. Well, actually, this problem isn't such a long one. I wasn't remembering it so well. The one way to do it is very fast. The amount of time that the trip will take at twice the speed is half the time, and the amount of the difference in time taken will be the original time minus the new time, which is half of the original time, which gives you half of the original time. So yeah, sorry if that confused you. I'm back before you were starting the second problem. It's yeah, originally years ago this was a more complicated problem, but yeah, in this form it's very simple. That's one way to do it. The the way starting from the definition without so if you do it without thinking, you know, if you just plug into the definition, average velocity is delta x over delta t. Delta t, therefore, if you solve for delta t, which is what you want, the time given the new velocity, new average velocity, you'll do what we did before, the same algebra steps. Multiply by delta t on both sides, divide by average v on both sides, and you get delta t is delta x over average v. You plug in the original distance divided by the new velocity or average velocity, you get the new time. And remember, when you're solving a problem, be careful to notice what the problem's asking for. In this case, if you called this the answer, you would happen to be correct. But what the problem is actually asking for is the difference in time, how much sooner. So if the numbers were different, the delta t that you calculate here would not be the answer. It's only that the numbers here coincidentally give you the same value as this delta t for the actual answer, which is the original time minus the new time to get how much sooner the arrival would happen. Okay, so here's another example. Again, on the definitions here, it's the definition of average acceleration that we're going to use. So it's question says, neglecting air resistance, how long does it take to reach 100 meter per second when falling from rest? You're given the value of the acceleration of gravity near the surface of the Earth. I'm going to use 9.8 meter per second squared, which the value varies slightly as you go from place to place over Earth's surface, because what's under the ground will be denser in some areas than in others. The ground will be shaped differently in some areas than others. So the values tend to be around 9.80 or 9.81 meter per second squared. So some classes will use 9.80, some will use 9.81. It doesn't matter. That 9.80 and 9.81 are the same to three significant figures. Or well, they're slightly different as three significant figures, I should say. Anyway, it doesn't matter. But I'm going to try to remember to use 9.80 so that we don't have to worry about coming out with different numbers. You know, if your numbers, if you're using 3 digits of precision in your values, and two people get different numbers in the third digit, it's just rounding error. It's probably just rounding error. So anyway, I'm going to use 9.8 if I remember to instead of 9.81. All right, right, and we use the fact that the average acceleration is equal to the instantaneous acceleration, the acceleration at any given moment, when the instantaneous acceleration is constant. In other words, if you're moving at, if the acceleration is 9.8 meter per second squared, then if that's the same at every moment in time, then if you take the average of a number that's not changing, you just get the number. That's all I'm saying there. So we want to find how long it takes to reach 100 meter per second, given the average acceleration and the value of velocity we want to arrive at, the 100 meter per second. So we just use the value, the definition of average velocity, and we want to solve for delta t. So it's the same algebra steps as before. Multiply by delta t on both sides, divide, in this case, by average a on both sides. And you get delta t is average v over, delta t is delta v, change in velocity, over average acceleration. The change in velocity is the final velocity, which is the 100 meter per second, minus the initial velocity, which is 0. I know that the initial velocity is 0 because the problem specifies that the motion starts, that the object starts at rest, meaning just that the initial velocity is 0. So the change in velocity is 100 meter per second, the final velocity, minus 0, the initial velocity. And delta t is that divided by average acceleration, which is the 9.8 meter per second squared due to gravity near the surface of the Earth. And so you wind up with 10.2 seconds for an answer. And, sorry, okay. So we got the 10.2 seconds in on the previous slide as the time it took to go from 0 to 100 meter per second falling. Now, at some point as you fall, you hit what's called terminal velocity, which is due to the fact that the air resists your falling through it. A lot of times I'm going to say neglecting air resistance, meaning that it's one less complication. We use the kinematic equation. So here, the definition of average acceleration we use without worrying about the fact that the air is slowing you down or slowing the object down a bit. And by the way, if you are falling, if you have a parachute, don't worry. Okay, so please try this. How fast are you going after falling for 5 seconds, having started from rest and neglecting air resistance? Oh, but by the way, air resistance becomes very important when you have a parachute because it's the air resistance that makes the parachute work to slow you down, right? So you don't, the fact that there's air resistance can be a very good thing. So yeah, please pause and work this out. Welcome back. Okay. I've got to come up with a better segue there. Anyway, welcome back from trying this. The solution to it uses the definition of average acceleration, and here it is. So how fast are you going? So you want to find the final velocity. And you know the definition of average acceleration, which is this. Average acceleration is change in velocity over change in time. So we're going to calculate the change in velocity in order to figure out what the final velocity is, which is how fast you're going. Or actually, the final speed is how fast you're going. I'll talk next lecture about things like differences between speed and velocity. Okay, so we want to solve for delta v first. So we want to get delta v by itself. To do that, we want to move the delta t to the other side. So we multiply by delta t because with delta t downstairs, multiplying by delta t will cancel it. And on the left side, we do the same thing to the left that we did to the right. So we wind up with delta t times average acceleration. And that leaves on the right delta v, which is what we want. So delta v is equal to what we got on the left, average a times delta t. Average A is the acceleration of gravity. Delta t is the 5 seconds. So you wind up with change in velocity is 49 meters per second. But we're looking for how fast are you going at the end. And so we don't want delta v. It's going to turn out to be the same number in this case, but for purposes of problems in which it won't be the same number, we start with delta v and we find the final velocity. So delta v, the change in velocity, is the final velocity minus the initial velocity. And the final velocity is what we're looking for, v. The initial velocity is 0 again, and I know that because I read the problem carefully, and it says starting from rest. So starting from rest means the initial velocity v sub naught is 0, and we calculated above that delta v was 49 meters per second, and so we wind up with the final velocity v minus 0 is 49 meter per second, or the final velocity v is 49 meters per second. Okay, I hope that that's been useful, and thank you for working through these problems, and I hope you have a great rest of your day.